Now, I'm going to, without any further reference, I'm going to demand certain properties of foliations of sutured three manifolds. So remember, gamma is a subset of the boundary of M and is a disjoint union of annuli and tori. And the foliations are to have these properties: transversely oriented, or as the three manifold people say, co-oriented. The components of R of gamma are leaves. Uh, Gamma is contained in the boundary of M. R of gamma is its closed complement in the boundary of M. And I don't remember if Rachel mentioned, but sutured manifolds come with a given transverse orientation of R of gamma. And that, of course, has to agree with the transverse orientation of F. Then F should be transverse to gamma, which is possible since gamma consists of annuli and tori. And the induced foliation by F on gamma is to have no two-dimensional rug components. And finally, the boundary components of A of gamma are the annuli in gamma, are also the boundary components of R of gamma and are convex corners relative to the foliation. So Rachel, next picture. There's a cross-section picture near one of the annuli in A of gamma. You see the transverse orientations. The lines are the leaves. And there are two corners, both convex with respect to the foliation. Next picture. Now, Rachel defined conic foliations for closed three manifolds, but for sutured manifolds, we need to modify the definition a little bit. So the definition is if each leaf of F either meets a smooth closed curve that is everywhere transverse to F, or a properly embedded smooth arc everywhere transverse to F, one end point of the arc in R plus gamma and the other in R minus gamma, then the foliation is said to be taut. Conlon, Roberts, and Kazez have shown that this definition is rather surprisingly problematic for foliations that are only integral to C0 plane fields. But we're going to be able to ignore this problem, so I will talk more about it. All right. Now, as Rachel told us, taut foliations have very important properties. I guess one that I've always found very surprising is Sullivan's theorem, that for smooth foliations, tautness implies that there's a Riemannian metric on the manifold making each leaf a minimal surface. Topologically important, each leaf is pi1 injective. Its fundamental group maps one-to-one into the fundamental group of the manifold under the leaf inclusion. And each compact leaf of the foliation has minimal genus in its homology class. The leaf basically defines the homology class in relative homology M comma gamma. The boundary of F is hitting gamma. And finally, there are no dead-end components. A dead-end component is simply a submanifold that's a union of leaves, and some of the boundary components are compact leaves. Some of the boundary components might be elements of key of gamma, transverse to the foliation. But the idea is that the boundary leaves are all oriented inward or all oriented outward. So a transverse curve starting outside the dead end component and crossing its boundary gets into it, it can't get out again and stay transverse. It has to turn around and become tangential at some point. So that's what a dead end component is. And Sue Goodman has proven not only that tautness implies there are no dead end components, but conversely, if there are no dead end components, the foliation is taut. And the topological information carried about taut foliations, bitaut foliations, is used by Gabai to solve some outstanding problems in the theory of knots and links. Next page, Rachel. Now, foliations can be very complicated, and the simplest are those of finite depth, which Rachel told us about. No leaf is locally dense or exceptional, and Rachel gave the standard definition of finite depth foliations, so I won't go through it again. The theorem of Gabai that interests me is that if a sutured manifold is taut, I believe Rachel defined that. It basically, the main thing is M has to be irreducible, and the components of R of gamma that are leaves, going to be leaves foliation, have to be minimal genus in their homology class, or minimal Thurston norm in their homology class, and irreducible. So that's an added condition on the definition of the sutured manifold. So if the sutured manifold is taut and no component of that manifold is a rational homology sphere, then Gabai says there is a taut foliation of finite depth on the sutured manifold. Next page. Now, these foliations were not claimed to be smooth, not even class C1. Apparently, in Gabai's construction, they are only integral to a C0 two-plane field. Now, that delicate problem about tautness raised by Conlon, and Roberts, it turns out, Rachel tells me, can be resolved by an isotopy. So Gabai's theorem makes sense. I think for many of us foliators, this problem that Conlon, and Roberts raised about tautness was very surprising. That foliations only tangent to a C0 two-plane field. There can be it could have no dead end components, but there could be another foliation tangent to exactly the same two-plane field, which has dead end components. Absolutely fantastic. But the problem can be, as I say, ignored, so we won't worry about that. Next page. Now, a renewed interest in foliations and contact structures amongst three manifold topologists makes regularity questions of interest. And it was thought that the well-known lemma of Nancy Capel would make it impossible for Gabai's construction generally to be C2 smooth. And it wasn't even clear that it could be C1 smooth. In fact, many, many years ago, David asked me whether his foliations were C1 smooth. I didn't have the foggiest idea because I didn't have the foggiest idea of how he constructed them. That was many, many years ago, thank God. Now, our main results can be stated very loosely as Gabby's foliations can always be constructed to be C infinity, can almost always be constructed to be C infinity, and always constructed to be almost C infinity. So there are a few things I need to define for you, what I mean by almost always and what I mean by almost C infinity. So first, almost always, I'm going to introduce the notion of a generic sutured manifold. It's a taut sutured manifold, non-empty boundary, and no component of R of gamma is a closed surface. If that holds, we'll say that M gamma is generic. That's because most of the sutured manifolds that actually are of interest and arise satisfy this condition. In particular, Gabby was interested in knots and non-split links, and the knot complements and non-split link complements are generic sutured manifolds. In those cases, the boundary of the manifold is the knot boundary or the link boundary. It's just made up of tori. R gamma is empty, so the condition is vacuously satisfied. Now, it's also useful to slice the knot or the non-split link complement along a minimal genus Seifert surface. And if you do that, you obtain a generic sutured manifold. And in this case, R gamma is the disjoint union of two copies of the decomposing surface. And gamma now is a bunch of annuli, the toral boundary components and the link complement or the knot complement have been sliced open longitudinally to become annuli. So those are the main examples that one is interested in. So my definition of generic, I think, is justified. Now, what do I mean by an almost C infinity foliation? A foliation of a three manifold is almost C infinity if it has a foliated atlas that's C1, but the atlas restricted to the complement of a certain finite union of closed leaves is actually C infinity. So furthermore, I require that along those few finite mean many closed leaves, the foliation be C1, C1 flat, and then of course, the foliation is C infinity elsewhere. So that enables us to state properly the theorem that I stated informally. If M gamma is a taut sutured manifold, no component of which is a rational homology sphere, that's so that there's enough topology to work with, then M admits a taut finite depth foliation, which is almost C infinity. So we can always modify Gabby's construction to produce almost C infinity foliations. Now, if in addition the sutured manifold is generic, the foliation has no closed leaves, and so by the definition of almost C infinity, it is C infinity. So that's the theorem I want to talk about. Okay, next slide, Rachel. Well, corollary of this that's important. Knot complements and non-split link complements have taut finite depth foliations, which are C infinity. Okay. Now, in order to sketch the proof of this theorem, we need to introduce some key ideas. Now, Rachel used the term groomed. I'm going to go through it again from a slightly different point of view. I want to talk about groomed junctures. Now, what do I mean by a juncture? So F will be a component of R gamma. So ultimately, F is going to be a compact leaf of the foliation I'm trying to build. Now, a juncture on F is simply a compact, properly embedded, transversely oriented one manifold, period. Now, where does this terminology come from? Foliation theory. If a depth 1 leaf, remember F, this component of R gamma is going to be a depth 0 leaf. If a depth 1 leaf, L, accumulates on a depth 0 leaf, compact leaf F, then the holonomy on F defines a cohomology class in the first cohomology of F. And that's surprisingly simple observation. If you start with a base point on the compact leaf F, look at a transverse arc, a compact transverse arc, issuing from that base point, and make it sufficiently short, then if L meets this arc at x naught, it will meet it exactly in points accumulating on x star. That's from the definition of depth 1. Okay, next slide.
Larry, you don't require smoothness on that last, is that last statement sort of a Thurston rigidity theorem about the homology class? Or the juncture?
I'm not quite sure I understand your question, Steve.
On the last slide, you had a homology class coming from a leaf spiraling in.
Yeah, and that's why I'm trying to describe that homology class. Because the holonomy of the leaf, if you restrict it to this set of points where L is intersecting the transversal and that are accumulating to the base point of the leaf, the restricted holonomy of the leaf to that set is infinite cyclic. And so that defines a homomorphism very simply from the fundamental group of the compact leaf to the integers.
But in the Thurston theory, you use the derivative to define that map.
This has nothing to do with derivatives. All of this works C0.
Okay, thanks. Okay.
But any such homomorphism, we know from algebraic topology, can be viewed as a one-dimensional cohomology class on F. Now, the geometric realization of that cohomology class is what I'm calling a juncture, a compact, properly embedded one manifold, transversely oriented. For every one cycle C, the evaluation of the cohomology class on C is simply the intersection product of the juncture with C, and that's Poincare duality. We don't need to go to Thurston for any of this. Now, if a leaf of depth greater than 1 accumulates on a leaf of depth at most 1, so F in this case is not compact, you again get a cohomology class very much the same way, but now Poincare duality produces a non-compact juncture. That's because in Poincare duality, on a non-compact manifold, ordinary cohomology is Poincare dual to infinite homology. That is, homology defined by singular chains that are infinite but locally finite. We're going to see an example of this, so that's why I'm mentioning it now. Next slide. Now, we go back to the compact case. So F is a compact surface, and actually it's one of these components of R gamma. Now, given a juncture J, a packet in that juncture is a maximal union of parallel, coherently oriented components. So given a packet, choose a representative of that packet and actually think of the packet as sort of collapsed to one of its elements. And these single representatives of each packet in the juncture will be called the supportive juncture and denoted by the absolute value sign. So one could think of the support of J as a kind of myopic view of J. You back off to where each packet looks like a single properly embedded one map. Next slide. The juncture is groomed if either it is a single packet of essential figure circles, that's shown in figure 1 below, where F is a two-hole torus, or J is a union of finitely many oriented, properly embedded arcs, such that for each component of the boundary, all of the arcs of J that meet that component have the same intersection number with that component. And that's illustrated in figure 2, where the F now is a 4-punctured disk, and the juncture has 4 packets. 2 of them contain 2 arcs, and 2 of them contain just 1 arc. But they all meet boundary circles the same, from the point of view of orientation, the same way. They have the same intersection number with the boundary circles. So that's what a groomed juncture is. Next slide. The support of the juncture in the previous figure is depicted here. In 1, where we saw a number of essential circles parallel, we see just they've been collapsed to 1. And in 2, where we had 4 packets, each has been collapsed to a single arc, and we have 4 arcs. So that's the support of the juncture that was just pictured. Next slide. Now, recall the notion of a decomposing surface in a sutured manifold. I won't go through it again, but S is properly embedded surface, and it meets the sutured structure nicely. And Rachel told us basically what that means. The thing is that if you have a decomposing surface, you can slice the sutured manifold apart along that surface, and Gabbai shows us how to give a sutured structure on the resulting manifold, which I'm calling M prime. So, and furthermore, very important theorem that Gabbai gives a rather obscure proof of. That's one of the things we're trying to clarify in work in progress. If M was taught, M gamma was taught, then decomposing by a decomposing surface produces another taut sutured manifold. So the decomposition is given by the notation I have there, that wiggly arrow. And we will say that the sutured manifold decomposition and the decomposing surface itself are groomed if for each component F of R of gamma, S meets F either in the empty set or in a groomed junction. So that's a groomed sutured manifold decomposition and a groomed decomposing surface. Next slide. Now, I want to go, the foliations are constructed by a kind of reverse induction using the hierarchy that Rachel told us about. But the inductive step is what I want to describe now. So suppose you have a group decomposition, M gamma to M prime gamma prime. And assume that M prime gamma prime has the kind of taut finite depth foliation that we want. Remember, I gave several properties of foliation would have to satisfy. So we first considered the case that F prime, the foliation on M prime, is smooth, and we try to use this decomposition to pull it back to a smooth foliation F on M itself, which is taut, has finite depth, and has the usual property. That's the goal. Next slide. Now, to do this, I want to talk about staircases. Gabai doesn't explicitly talk about them, but they're lurking. And I believe the notion of staircase was first introduced by Nishimori. So I often will call these Nishimori staircases. Now, how do we construct a staircase? So we have F, a component of R gamma, and we look at a normal neighborhood of F in the manifold M. And we let J in F be a juncture. Now you cut apart along the support of that juncture cross 0, 1. The result contains two copies of the juncture cross 0, 1. I denote them with a plus and a minus sign. And if X is a point of J, you get two corresponding points, X plus or minus, in the two copies of the support of J. Now you reglue by a diffeomorphism F bar, taking J plus cross the interval to J minus cross 0 to F of 1, because F is a contraction, taking 0, 1 to 0 F of 1. It's a contraction to 0, and it's C infinity tangent to 0, to the identity at the point 0. So the result is called a simple staircase, or as I often say, a Nishimori staircase, and it looks locally like the following figure, Rachel. So there it is, cross section. You see the dotted line is where we did the gluing. The horizontal lines are the product foliation of the normal neighborhood, but now it becomes a depth 1 foliation. The black circle represents the support of J that we have cut apart along and then re-glued. The dotted line indicates where the gluing takes place. And the product foliation induces a C infinity foliation of the simple staircase. So the horizontal lines, you see them exiting the figure on the left, and they're coming back into the figure on the right, but closer to F. So we're getting depth 1 leaves, except at F itself, which is a depth 0 leaf. And we have a foliated manifold with corners, a convex corner and a concave corner. E is called the entrance to the staircase, and F is called the floor of the staircase. Now, since F is a contraction, this is a depth 1 foliation. Okay, I think we can go to the next slide. Now, as I've been saying, I like to call simple staircases Nishimori staircases. We're going to be dealing with very non-simple staircases soon. Now, the smoothness of the foliation where we glued to J plus cross 0, 1 to J minus cross 0, 1, that dotted line in the previous picture, is slightly problematic. You know, when you're gluing with a diffeomorphism, but you don't want the leaf, you want the leaves to meet nicely, smoothly. That is a fairly easy problem to deal with, and a careful treatment is given in the book I wrote with Alberto Candel, Foliations 1, section 3.3.A. So I'm going to ignore this technical problem with smoothness. So when I glue transverse pieces of foliations together by diffeomorphism, I will assume the result is smooth because it can be proven, it can be done that way. All right, next slide. Now the entrance to the staircase is J cross F of 1, 1. Remember, F is a contraction to 0, so F of 1 is less than 1, and that's the part where the foliation begins. It's either going to be a union of rectangles, one for each component of the support of J, that's when J is a bunch of arcs, or it's going to be a single annulus, that's where absolute J, the support of J, is a single circle, essential circle. Each component of the entrance is foliated as a product. I think that's obvious. And I've already said I'll call F cross 0, the floor of the staircase. So I think we can go on. So here's S meeting F. Now S might have several components, or those two pieces of S you see might belong to the same component. The thing is, it's meeting F in a groomed juncture. Now in this case, the two black circles are representing either two parallel arcs or two parallel essential circles. Excuse this vertical line in that slide. I think my drawing software decided to drive me crazy by introducing it, and I have not been able to figure out how to get rid of it. It's irrelevant. Now, where S meets F, we erect the staircase and we deflect S so that it meets the entrance of the staircase as indicated there. Okay, next slide. Now, so I've slightly displaced S so that it enters the entrance. Now the region complementary in M to the staircases and S is an isomorphic image of M prime, throw away our gamma prime, under an immersion of M prime into M. The picture is below. On the right, we see M prime preparing to immerse into M. And on the left, we see the immersion is completed. So M prime now, remember, carries a smooth foliation. And it's meeting these vertical parts of the boundary of M prime transversely. Those vertical parts are either rectangular segments of annular sutures or they're complete annular sutures, according to whether the entrance to the staircase is rectangular or annular. So what we want to do is continue that foliation F prime of M prime into the staircase. Okay, next picture. Now, if the entrance to the staircase is a union of rectangles, each of those rectangles meets the boundary of M prime in a union of rectangular segments of some of the annular sutures. Since the foliation induced on gamma prime is assumed to be redless, these rectangular segments are foliated as a product. And so after a smooth isotopy, F prime actually matches up with the foliation of the entrance to the staircase and just continues by the depth one leaves in the staircase to a smooth foliation. Now, if E is an annulus, there can be problems. But if the annulus meets the boundary of M prime in annular sutures, well, it does. If F prime induces the product foliation on these sutures, then the staircase foliation will match up with the foliation F prime and continue F prime by the spiral ramps to a smooth foliation. That's if the foliated annulus is trivially foliated. Not generally the case. Next slide. So it's possible that F prime meets one of these annular components of gamma prime in spirals, or in a combination of spirals and circles. Then the Nishimori construction is no good, because it should be a product foliation along that annulus. So let me give you an example. Suppose F, the component of our gamma, is a torus, and that A, the annulus, is foliated by two boundary circles and infinitely many spirals. So the staircase will need to be foliated so that the entrance is foliated by spirals and the two boundary circles. The construction of the foliation we gave, the Nishimori construction, doesn't do that. The boundary circles will continue as a spiral ramp, diffeomorphic to a half-infinite cylinder winding in on the torus. Depth one. But the spirals will continue as half-planes, winding in on the cylindrical depth one leaf, as pictured below. Picture. There it is. So a segment of the cylindrical leaf, the depth one leaf, is drawn at the bottom part of the picture. S1 across the half-infinite interval. And above we see one of the two planes, is actually a strip in the two plane, winding around this segment of the depth one leaf. The other part of the strip is winding out on a cylindrical segment of the same depth one leaf. It takes a little thinking, but you can actually more or less picture what's going on if you think about it. And notice that J, the base point across zero infinity, is a juncture for the depth two leaves. Depth two leaves are half planes winding around this half cylinder. Incidentally, when I was giving a talk many, many years ago at a seminar at WashU, Gary Jensen nicknamed this foliation the toilet paper foliation, for reasons, I guess, that are obvious. Okay, now the non-compactness of the juncture J makes it impossible for this foliation of the staircase to be C2. That's by a theorem of Cantwell and myself. We showed that if all leaves of a foliation are at finite depth, then it is C2, it's a C2 smoothable if and only if all junctures are compact. And here we have a non-compact chunk. And actually, C2 smoothable in this case turns out to be C infinity smoothable also. Next slide. So in this case, you really don't need that theorem by Conlon and myself. We can appeal to the well-known lemma of Nancy Capel. And actually, the work that John and I did was a vast generalization of the Capel lemma. So after a little thought, you can see that the holonomy of the depth 0 torus F is generated by commuting homeomorphisms F and G, where F is a contraction to 0, and G has fixed points, which are exactly the orbits of 1 or under the iterates of F. By the Capel lemma, F and G cannot both be C2 diffeomorphisms. Thus, the depth 2 foliation of this staircase, which seems to be forced upon us by Gabai's construction, cannot be C2. Now, by an old construction of Dennis Pixton, you can choose these F and G to be C1 diffeomorphisms and C1 tangent to the identity at 0. So this staircase can be made C1 and C1 flat at its floor. So this leads us to conjecture that Gabai's foliations can be constructed to be C1. However, it doesn't follow from Pixton's construction, because generally the annual entrance to the staircase might have to be foliated by a combination of circles and spirals, and Pixton's construction does not work here. So an annulus foliated by circles and spirals can be obtained from a rectangle with the product foliation. You go one edge to the other edge by a diffeomorphism, as indicated. The fixed points of G gives circle leaves. The points not fixed give spiral leaves. So look at the figure below. There, next figure. Rachel, next figure.
Sorry, I've scrolled it and it's, oh, there it goes. There was a delay.
There we are. So see the rectangle at the top, trivially foliated, and G bar glues it to give us a foliated annulus, in which, in this case, G itself had 3 fixed points, the 2 endpoints of the interval and a point in between. So we got 3 circle leaves, 2 boundary leaves, and 1 in the middle, and the rest of the leaves were spiral. But things could be much more complicated. G could have many fixed points, there could be many circle leaves. We could split into many copies of these spiraled pieces. Now, in general, this foliation of the annulus is a foliated interval bundle over the circle, and G is simply the generator of the total holonomy group. Next slide. Rachel?
Yeah, unfortunately, I'm scrolling ahead and it's not updating on the screen. I don't know what the issue has become. So on my screen, I see the next slide, and on here I don't.
There is a delay with their website between what's shown on the YouTube feed and what's shown on the Zoom. They're different.
So but you can't see the next slide, can you, Steve?
I see a foliated interval bundle over S1.
Oh, okay. I scrolled to the next page.
That's all I see too.
Yeah, no, I've scrolled to the next page and it's not showing on the screen. Does anyone have any suggestions?
Light a candle.
I could try leaving and then
I have
joining
no
again
idea
and
what to
see if
do.
that wakes it up.
No, that's weird. I see your screen. It says I'm viewing your screen and I'm looking at it on Zoom.
Yes, and it's showing the annulus picture, right? This is a foliated interval bundle. But on my screen now, I've updated to the next page. Like I did before, it finally did update without me
Certainly,
doing anything. Now it's not.
probably their server.
Let me.
Well, when you have no idea what to do, my strategy is to stop and come back again.
Yeah, that's what I decided to do. Thanks.
Maybe we stop sharing and then start again.
Okay.
Okay, new slide.
Okay, what was the previous slide? Let me get oriented here. Okay, that's what you had. All right.
Yeah,
F prime is C infinity and C infinity flat along the leaves. So we can assume that the foliation of the annular entrance is C infinity and C infinity flat along the circle leaves. And so to produce this foliation of the staircase, you need commuting homeomorphisms, F, a contraction to 0, G, homeomorphism, leaving F of 1, 1 invariant. That's where the entrance of the staircase is going to be. And it should be C infinity on that interval and C infinity tangent to the identity at its fixed points in that interval. With that, that can be produced by results of Bonatti and Farinelli, and they depend also on results of Navas. A pair of homeomorphisms can be found which are C infinity on the almost full interval, just excluding 0, and C1 and C1 tangent to the identity at 0. So with this, we can extend the foliation F prime into this bad staircase to a foliation that's C infinity, except at the floor of the staircase, where it is only C1 and C1 flat. Those would be the components on which the juncture is a packet of essential circles, forcing a staircase with annular entrance. It seemed that this would be best possible, but you could smooth Gabbi's foliations except perhaps at finitely many compact loops. But John Cantwell, bless his soul, came up with a really ingeniously simple trick to proceed if the floor of the staircase has non-empty boundary. And that's where the genericity condition comes in. So here's an example. Suppose that the component F of R gamma has non-empty boundary. One of the components is C. We assume that the juncture has support, which is an essential circle. Well, here's an example. F is a one punctured torus. The juncture is pictured, the support of the juncture, and the boundary of the torus, C. I've also added an arc there, a dotted line. It has one endpoint where it intersects the support of the juncture, the other endpoint where it intersects C. And so if I cut F apart along the support of the juncture, I get an F prime, in which tau is a properly embedded arc. All right, next picture, or next slide, yeah, picture. So here's the relevant part of F prime cross the interval, right near the juncture. I've split it I've split along the junction and crossed with 0, 1. Or I've split along the support of the junction and crossed with 0. I don't show the foliation. Right now it's the product foliation. I show a rectangle grayed out, rectangle tau cross 0, 1, and it is meeting the product foliation in arcs parallel to tau. All right, next picture. Now in the picture, F prime results from splitting, as I've said that. Okay, what is new here? I guess if we've used F as a contraction, we've used, so if we had just re-glued by F bar, we'd get the Nishimori foliation and the entrance to the staircase wouldn't be properly foliated. So before re-gluing with F bar, we're going to split F prime cross 0, 1 along that grayed rectangle. So the next figure, Rachel. See, I've cut it apart along there. And I'm going to glue the rectangle to its, the one copy of the rectangle to the other one by diffeomorphism G bar. Next slide. So the diffeomorphism G bar is basically just the G on the interval 0, 1. It's to be a diffeomorphism. And it's to match the foliations. It matches the foliations perfectly, so you get a new foliation of F prime cross 0, 1. And if we choose G to be the identity until you reach the entrance to the staircase, so the identity on the interval 0 to F1, and then we have the holonomy we want on the entrance of the staircase, I'm calling it G1, this all fits together. When you glue with F bar, you're just gluing the product parts together. So you get a depth 2 foliation, and it's G infinity. Next slide. So the circle leaves on the entrance annulus were C infinity flat. So G1 with C infinity tangent to the identity at its fixed points, in particular at its endpoints. So it matches smoothly with the definition of G being equal to the identity from 0 to F of 1. Now, so I think I've said everything that needs to be said. The re-gluing produces a staircase so that the entrance is foliated by the appropriate collection of circles and spirals. Everything is C infinity and C infinity flat, except at the floor of the staircase where everything is just C1. Well, no, excuse me. Everything is C infinity. Excuse me. I got lost there for a minute. G was a diffeomorphism. So we've actually gotten a C infinity foliation of the staircase that meets M prime, the foliation F prime of M prime, appropriately in spirals and circles. Okay, next slide. So on the depth 1 cylinder leads, tau lifts to a compact juncture. So that fits with the theorem that John and I proved years ago. And it's only possible to have this compact juncture because I assumed that F had non-empty boundary. And that's basically the genericity, the generic condition for sutured manifold. Just for information, the depth 2 leads in the punctured torus picture look like this. Those ends, infinitely many ends, which are punctured half cylinders, are winding in on the punctured torus. And the two edges of the leaf are the spirals, one of them spirals on the entrance to the staircase, the other is spirals on the annulus, which was C across the interval. Anyway, it takes a little thought, but you can actually see this. Next slide. Now, here's how things go, the inductive construction. You start with the taut sutured manifold and you use the hierarchy that Rachel told us about. Now here, each SI is a groomed decomposing surface, and Mn, gamma n, is a product sutured manifold. Actually, Rachel required it be a bunch of product sutured balls, which is fine. If you have product sutured manifold, you can further decompose in the product sutured balls, but for constructing the foliation, all I need to know is that Mn gamma n is a product sutured manifold. Now, if M gamma is not generic and has non-empty boundary, we're going to construct an almost C infinity foliation on M with all the desired properties, and the closed leaves will be components of R of gamma. If M is closed, then the first decomposing surface is a closed surface, and R of gamma 1 consists of two copies of that surface. If the desired almost C infinity foliation has been constructed on M1, it is C1 flat along R of gamma 1, so we can reglue the two copies of F1, of S1, to give an almost C infinity foliation on M. Okay, next slide. So, the product foliation on Mn, the end of the hierarchy, trivially satisfies all our conditions. It's finite depth, 0. It's smooth. It's C infinity flat along all leaves. And it induces reckless foliations on the sutured boundary. This will start a reverse inductive construction of the foliations F5 on Mi. And use the process I've just outlined for the inductive step. F equal F naught will be the foliation we have been looking for as we go back up the hierarchy to the beginning. Next slide. Now, if M gamma is generic, all of the Mi gamma i's are generic, and we've outlined a detailed proof that if Mi minus 1 has a smooth foliation with the desired properties, so does Mi. In the non-generic case, one has to use reverse induction and the theorem of Bonatti, Farinelli, and Navas to obtain the desired almost C infinity foliation. And in all cases, the tautness of the foliations is easily proven using Goodman's criterion, quad erat demonstrandum. That's the outline of the proof. And happy birthday to Paul. Thank you all. It was an honor to be asked to give this talk. Thank you.
Are there any questions?
Well, this is obviously great news after all these years not knowing really if if all this could be made C infinite. Please, I didn't get it. Maybe you said it. I'm sorry. I didn't get it. Was the passage to C infinite an approximation? Are the plane fields close to each other, or do you have to do something a little more sophisticated? Well, I mean, it is sophisticated, but do you have to move really?
This is not sophisticated, actually. It's just complicated.
Is it an approximation? Is the smooth foliation C not close to Gabai's one?
That I don't know. Gabai's construction, he simply doesn't worry about smoothness. And so when he has the entrance, he doesn't talk about staircases, but it's there. When he has those spirals and circles, he just extends. And you can only do that. The best you can hope for would seem is to produce a foliation integral to a C0 two-plane field. Our construction is different at this point than Gabai's. We don't just extend, we very carefully find a way to extend into the staircase. So I don't think I can compare his foliations to these in any rigid sense. It's probably not true that his construction without any modifications produces something isotopic or approximating in some reasonable sense the foliations I'm talking about. This is a way to modify Gabai's constructions to get smooth foliations.
Thank you, Larry.
What?
Okay, so any further questions to Larry? Okay, so you have.
It's not a question. I'd just like to say, Larry, how wonderful this is to see this work. And I've heard you talk about this on other occasions. It's so beautiful. So thank you very much.
Oh, you're welcome. Thank you.
Okay, so let's thank the speaker again.
You're welcome.